Think you know Jupiter? Think again. For decades, we pictured the giant as either a bottomless ocean of gas with no heart, or a planet wrapped around a rock ice seed as hard-edged as a diamond. Then NASA's Juno skimmed above the cloud tops, listened to Jupiter's gravity, and showed both pictures were wrong. Jupiter's heart is neither solid nor missing. It's diffuse, fuzzy, and that simple truth rewrites its origin and magnetic personality. New here, subscribe to Quantum Leap. We dive deeper in seconds. Here's the setup. Two rival ideas used to rule the conversation. In one, Jupiter formed quickly from the direct collapse of a cold cloud of gas. No core required, just a titanic sphere of hydrogen and helium all the way down. In the other, called core accretion, a heavy kernel of rock and ice formed first, made of elements like oxygen, silicon, magnesium, and iron. That kernel grew until its gravity pulled in vast amounts of gas. That second story predicts a compact, dense core with a crisp boundary beneath the swirling atmosphere. Neat, clean, and wrong. Juno's mission was built to test reality. Launched in 2011 and in orbit since 2016, Juno loops over Jupiter's poles on a long, narrow path that dives to within about 4,200 kilometers of the cloud tops. Every pass, it beams a steady radio tone to Earth. As the craft flies through tiny ups and downs in gravity, that tone shifts. From changes as small as 0.01 millimeters per second, scientists reconstructed a gravity map 100 times sharper than anything before, a direct fingerprint of how mass sits inside. It's classic Doppler work. Stronger gravity tugs Juno faster, so the tone shifts higher. Weaker gravity lets it lag, and the tone dips. Stack dozens of passes from different angles, and you can turn those tiny pitch changes into a three-dimensional portrait of Jupiter's interior. And the picture that emerged shocked everyone. Instead of a tight, well-defined core, the data revealed a wide, dilute region where heavy elements blend with hydrogen and helium across a huge volume, reaching roughly half of Jupiter's radius. There's no sharp boundary. It's a gradient, like cream in coffee. That rattled formation theories. If core accretion needs a solid seed, why does the heart look dissolved? If collapse needs no core, why the enrichment in heavy elements? A dramatic fix tempted researchers, a giant impact that shattered an early compact core and mixed it upward. But supercomputer crash tests kept settling the debris. A sharp boundary reformed. The interior refused to stay fuzzy. The impact idea wasn't the easy answer. Then a clue arrived from next door. Saturn, the ringed neighbor, turns out to be a seismology experiment in plain sight. Waves in its rings record vibrations from deep inside the planet, the way earthquakes reveal Earth's interior. Combine those ring seismograms with precise measurements of Saturn's gravity, and you get a consistent picture. Parts of Saturn's deep interior don't convect. In other words, they aren't churning and mixing efficiently. That naturally produces a compositional gradient, a fuzzy core. And Juno's own maps suggest Jupiter also has large regions that resist convection. That's a big deal. If a gas giant were fully convective, heat would rise and fall and mix the interior into a fairly uniform soup. No dense central region would survive, but if some layers are stable, held in place by subtle gradients of temperature and composition, heavy elements can remain smeared through a broad middle, neither clumped into a hard core nor erased by vigorous mixing. In that picture, fuzzy cores aren't mistakes. They're natural outcomes of how giant planets grow and cool. Okay, but how does that square with Jupiter's magnetic weirdness? This is where the story gets even richer. Deep below the cloud belts and the Great Red Spot lies a sea of liquid metallic hydrogen, a phase where hydrogen's electrons roam freely, turning the fluid into an electrical conductor. Spun by Jupiter's 10-hour day, it powers a dynamo, inflating a magnetosphere that stretches downwind for millions of kilometers, brushing even Saturn's orbit. Yet the field isn't tidy, it's lopsided and patchy. The northern hemisphere hosts intense magnetic spots. The south seems weaker overall, and some models even describe two magnetic south poles. Jupiter is the biggest, strongest planetary magnet in the solar system, but it isn't the neatest. Down there, Temperatures can exceed 30,000 Kelvin and pressures soar to millions of times Earth's. In that furnace, hydrogen behaves like a metal. The resulting magnetosphere balloons to 7 to 21 times Jupiter's diameter on the day side and flares into a long tail at night. Maps even hint not just an offset dipole, but extramagnetic patches, including a second southern polarity. It's a magnet gone baroque. You might hope a fuzzy core would explain those quirks. Ironically, a fully stable dilute core makes the mismatch worse. Models work best when a shallow, stable layer higher up modulates the flow beneath, like a lid reshaping the boil. Add one more twist: helium rain. Under some conditions, helium separates from hydrogen and drizzles downward, tweaking conductivity and currents. Partial stability plus helium rain points to a more complex, more plausible dynamo. But the full recipe is still a mystery. If you're enjoying this deep dive, a quick ask: tap subscribe so you don't miss the next chapter. It helps more than you think and tells algorithm you want more. Back to the giant. One lesson is already clear: interiors are messy, and that mess matters. Old models treated giants like orderly layer cakes that cool in predictable ways. Fuzzy cores disrupt that timeline. A gradient of heavy elements stores and releases heat differently, changing how a planet shrinks and dims over billions of years. The ripple reaches beyond our solar system. Many exoplanets we found are gas giants or subgiants. Every time we measure mass and radius, we're judging an interior. Knowing that real giants can carry broad, fuzzy hearts will sharpen those judgments and may explain worlds that once looked too puffy or too dense. What about the auroras? If Jupiter's magnetic field is the loudest in the planetary orchestra, its auroras are the laser show. Fueled by the dynamo and by charged particles whipped around by the spinning magnetosphere, Jupiter's polar lights blaze in ultraviolet all the time, hundreds of times more energetic than the glows we chase on winter nights here on Earth. They never turn off. Ultraviolet time lapses from Hubble reveal curtains of light whipping around the poles, flaring and fading as the magnetosphere interacts with the moons and the solar wind. These are not gentle glows, but powerhouses, hundreds of times more energetic than ours, fueled by a dynamo the size of a world. So what likely happened? Neither extreme, no core, or hardcore fits. Jupiter probably grew from both heavy elements and gas in an intertwined way. A seed formed, then dissolved partly into the hydrogen-helium envelope. Partly stable layers slowed mixing, leaving a heart richer in heavy elements toward the center and leaner outward. A long fade instead of a crisp line. That's a fuzzy core in plain language. Here's a thought experiment to make it tangible. Imagine dropping a sugar cube into hot tea. At first, there's a sharp boundary between cube and liquid. Then, as the sugar dissolves, a gradient forms, sweetest at the bottom, milder above, no clear line. Now imagine the tea is stratified so the layers don't mix efficiently. That gradient lingers. Jupiter is cosmic tea, and its sugar is oxygen, silicon, iron, and friends, dispersed through a deep interior that prefers gradients to hard edges. Tell me in the comments which giant planet mystery you want next: Saturn's hexagon, Uranus's tilt, Neptune's supersonic winds, or the hunt for metallic hydrogen in the lab. Your ideas genuinely shape what comes next. Plenty remains. Is the fuzzy core permanent or slowly dissolving as heat leaks out? How does the gradient couple to the metallic hydrogen ocean above? Which layers are truly stable and which only mix slowly? Juno gave us the outline. Filling in details needs more passes, better models, and new missions with seismology, microwave mapping, and sharper gravity. We also need lab work on hydrogen-helium under Jupiter-like pressures to test helium rain. Even the magnetic puzzle is open. A shallow, stable layer may reshape the flows that power the dynamo, but we don't yet know its thickness or how it evolves. This is why Jupiter matters. It's a Rosetta Stone for planets. A fuzzy core shows formation is not a simple switch, but a spectrum tuned by chemistry, temperature, and time. It reminds us to be humble about neat stories and excited because complexity is honest and interesting. The king of planets is more intricate than we imagined, And that's good news. Nature is giving us more information, not less. Let's end where we began, above bands that look serene from far away. Underneath, storms the size of Earth roll. Lightning cracks through ammonia clouds, and a radio beacon hums from a hidden ocean of metallic hydrogen. In the middle sits a heart that isn't a wall, but a blur, where the heavy stuff of rocks meets the light stuff of stars and refuses to draw a hard line. That refusal changed our minds, and it will change our models and how we look at every giant planet we've found. If long-form cinematic deep dives into space science are your thing, tap like, subscribe, and share this with the friend who always asks the sharpest questions. I'll see you in the next episode.